So, yes, no, I'm not that person. But I now. But yeah, I know the first time.
All right, everyone, we'll go ahead and get started. Pleased to have Dr. Ashley Cabas here today for the forum, and Dr. Dan Obenauer is online, and he's going to do the introduction. So I will turn it over to Dan.
Hello, can you hear me?
Yes.
You can? Yes?
Yes.
Yes.
Okay. All right. Well, oh, good. I'm honored to have the opportunity to introduce today's speaker, Dr. Ashley Cabas. Ashley is one of my faculty colleagues in the Department of Civil Construction and Environmental Engineering, and she is also, of course, a faculty fellow in the Center for Geospatial Analytics. Her research is in geotechnical engineering with an emphasis on seismic hazards, and she'll talk a lot more about that today. She completed her bachelor's in Venezuela and received a master's and PhD at Virginia Tech. She is the recipient of numerous awards, including most recently the NSF Career Award and the Virginia Tech Outstanding Young Alumni Award. Dr. Cabas is also a founder of the Earthquake Engineering and Seismology community in Latin America and the Caribbean. So really excited to see her presentation today.
Thank you, Dan. And I'm going to share my screen again because maybe this one. Can everyone see the presentation online? Or do you see you can see it? Are they seeing the speakers? Display setting. Presenters view.
Yep.
Okay, I think they're fine. And then you can also see it. Let me see if I change. Yes. Fantastic. So good afternoon, everyone. Thanks again for coming here. Thanks again for the invitation. It is my pleasure always to come here and learn from you and interact from you all. As Dan mentioned, let me see if as Dan mentioned, I'm an assistant professor in the Department of Civil Construction and Environmental Engineering, and I am thrilled to share with you some of our research questions and more recent research questions on the issues of spatial variability of ground motions and ground deformations. And that is what I am I'm hoping to share with you today. These are the people responsible for the magic, and all of the work that I'm presenting today, all of the work that I'm most proud of is really coming from an amazing team. And then today, more specifically, I'm going to be talking more about a couple of projects led by two senior PhD students in my lab, Cristina Lorenzo Velasquez and Nancy Gaviria Bayo. Our lab has grown and continues to grow, and that also makes me very excited, but we've had already some alumni with very successful trajectories in industry and academia. So our geohazards and earthquake engineering lab has two overall goals, or two main objectives. And one is to engineer resilient urban systems and critical infrastructure to seismic hazards, understanding hazards as both ground shaking and ground deformation. And then we care about that, about reducing those risks associated with that hazard, specifically or particularly for those vulnerable communities where we have seen in past earthquakes a disproportionate impact of these events. Given all the other things staying the same, vulnerable communities tend to have a harder struggle in recovery times and overall effects in their failures. Civil infrastructure failures. So today I was excited, or I am excited to share three pieces of our journey as a lab. One is my personal geospatial story, how I've been using geospatial analytics, how that has actually shaped some of the research questions that I'm most interested on right now, and then how we use geospatial analytics in current projects. and just sharing, concluding remarks on how I think geospatial analytics can shape the future, at least in the fields where my team currently does some work on. So as Dan mentioned, I did my PhD at Virginia Tech, a magical place. And my PhD focused on understanding complex wave propagation phenomena and the impact of local soil conditions and rock conditions on ground shaking characteristics. This topic had a very site-specific lens to it. I wanted to understand what a soil column can do to important characteristics of ground shaking, namely amplitude. Is this soil column amplified, de-amplified, the amplitude of these seismic waves? Frequency content, how is the seismic energy produced by a seismic source being distributed across different frequencies? That matters to us engineers because different pieces of civil infrastructure respond differently to different frequencies. So we really want to understand from the ground motion perspective, how is that energy distributed? And then duration. Duration was key and is key for understanding cumulative damage in different civil infrastructure systems and also in soil columns. Some fatigue may happen, degradation of properties of the materials for longer duration ground motions than shorter duration ground motions. So those three aspects, amplitude, frequency content, and duration, those can be a function of local soil conditions. So that's pretty much where I lived during my PhD. While I also understood that seismic hazards vary globally, right? And this is coming from a global earthquake model produced by the GEM group, where for rock conditions, so here they're not considering the impact of local soil characteristics. These are all rocks parameterized by the same condition. We will talk about that in a minute. You can see that there is a variation in the hazard, the threat from earthquakes. So while I was very interested in understanding the fundamentals of wave propagation, I also knew that there was more to it. And that more was that incorporation of something that was very local, very precise and constrained into a broader, larger regional scale. Within my PhD, I didn't get to that incorporation. So of course, that's where I started my journey at NC State. And it is a very complex question, I have to say. And it only became more apparent shortly after I arrived in 2018 with an earthquake in Anchorage, Alaska in 2018. It was my dream, I have to say. After a large magnitude event happens, many teams mobilize to do reconnaissance and learn from the damages after that earthquake. As a PhD student, I wanted to see it. I wanted to, of course, never or understanding the devastation and the negative effects on the communities. I really wanted to learn and see, for me, what I was studying, how that could impact the safety of communities and civil infrastructure. So I had that opportunity. I was invited in 2018 to collect perishable data and document case histories from this earthquake. And it was a large magnitude earthquake, but in Alaska, those aren't uncommon. So a 7.1 earthquake happens on average once a year. What was unique about this one was how close it was to a densely populated city, Anchorage. So this particular earthquake, no loss of life, that was good. And then very minimal damage to civil infrastructure, offer an opportunity to study success stories, success performance of civil infrastructure. Yes.
Do you remember how deep that quote was?
Do I have it there?
Oh,
yeah, 11.3. Oh no, north of downtown. I don't remember, Carl, but I can.
that's okay.
Yeah.
Yeah.
I don't think it was.
Kind of surprising it's actually that close.
Mm-hmm.
It's a bit surprising there were no deaths. Being that big.
Yeah, no, the ground motion wasn't as high either. So yeah, a very interesting case study. They were also expecting more landslides as well, but the duration wasn't there, wasn't as long, and then the peak ground accelerations weren't as high either. What was really interesting to me and quite unique, because so far I had only studied the ground motion side, was to see ground failures. And these are some cracks, ground cracks from, triggered by the earthquake. This is me here standing there and really trying hard to measure the ground crack length, the depth. I was really into my job until my colleague from BYU came with his drone and really captured the important feature. So that was a very real moment for me when I'm like, oh, I'm missing something important if I don't understand the larger scale aspects of ground deformation. And in this particular earthquake, those because there was minimal damage from the ground shaking, most of our reconnaissance really was focused on understanding the ground deformation side. And then that was the point in my career where I really understood that it is the connection of both that will bring a real reduction to seismic risk. So that was an important moment, I would say. And there was a paradigm shift for me. I think that seismic hazard and risk calculations, assessment, and individual locations are still fine. They're okay for buildings or structures that can have that small enough spatial extent. It's small enough that we can assume that the ground motion that seismic demand is uniform across those dimensions of interest. But then this reconnaissance, understanding the effects of earthquakes at a community level, really made me feel, what if my target now, what if my research question is now centered around large distributed infrastructure? Think lifelines, think water distribution systems, bridges, power distribution systems. When you look at those, now you will have different inputs at different locations, and now those spatial correlation across the occurrence of different intensity measures, those will start to matter. Whereas for a single location, we really weren't looking at those. And then the stakeholders, people that care about what's happening to this large distributed infrastructure have also changed. Now we're talking about governments, infrastructure system operators, and then insurers for property portfolios. And around that time, because I was so intrigued by this complexity, understanding why propagation at a single site was so difficult. And now there I was saying, well, it's not enough. I really need to understand what's happening at larger scales, which are the systems affecting communities. So I was very lucky, and still am, that the Center for Geospatial Analytics was here to support me in my writing proposal process, in my thinking process, realizing the big challenge. Well, what I'm excited about is about characterizing highly variable and uncertain hazards across multiple scales. And at the same time, I need to understand that system level performance of that civil infrastructure. So this is now the space where I live most of my days in my professor life. And I'm glad that that's the direction our team has come. I will talk more about the details. This is just to show you just a mix of different research outcomes from my team when we're really now getting into regional assessments of hazard, regional characterization of the spatial variation of soil conditions. It's not just that one soil column anymore. We really want to understand what's the influence of the whole environment. And that has also led us to incorporate more of the geology and engineering geology aspects in our work. So it has been a very exciting journey for me. And the last pivot also came from a recent earthquake in 2021 in Haiti, where again, I did some reconnaissance for or after the earthquake. And we quickly realized, all the engineers in the team, that understanding the spatial variation of ground shaking, measuring ground deformations was not going to be enough for Haiti. Was not going to be enough to understand the full impact on these communities. We really needed to understand the multiple crises that Haiti was going through to fully describe the impacts of this particular earthquake. And I have a few thoughts on that toward the end. So we're not done yet with that journey, but I'm really excited of where things are taking us. And then with that, I wanted to give you more specific examples of how we're using geospatial analytics, some of the projects that my wonderful students are leading, and then how we're really gaining different insights and gaining a deeper understanding of the type of patterns in the data that matter the most for our engineering designs. So our team uses geospatial analytics to understand spatiotemporal variability of ground shaking and deformation. I will focus on the spatial piece for this presentation, but we're also looking into how these ground motions, how the fabric of the soil changes, given the how they are subjected to different deformations in a given period of time. And then we don't stop there. As I said, we really want to model their impact on civil infrastructure and the communities they serve. That has also been something that I felt enabled to ask as a researcher, because now I care about who's in the building when the earthquake happens. I really want to my research questions to reflect the performance of the structure, but also the potential for recovery of those communities. And we do that through interdisciplinary research, are really trying to break those disciplinary silos, innovative solutions to ground societal challenges such as reducing seismic risk, prevent loss of life, and economic loss. And then we found that these tools and approaches to identify these patterns in the data and communicate those to decision makers was really going to become the game changer for our life, for our lab, and for our outcomes to have a more impactful benefit in practice. So with that, let's talk about spatial variability in ground motions and what that means to us. What you have on your left, and I don't know how easy you can see it, but let's see if you can see my cursor. I think they can see it online, but you don't. What you have on the left is called a shape map, and it's providing the geographical distribution of ground motion intensity. So you probably cannot see the contours very well, but closer to the fault rupture, there should be a stronger ground shaking intensity, and that makes sense. And this one, I should say, is corresponds to one of the recent earthquakes in Turkey this year. So in red, I don't know if you can see it very well close to Adana, we have the strongest ground shaking. And typically, what you will see with earthquakes is that the further away you are from that epicenter, that fault rupture, you will see a reduction in ground shaking intensity, right? That's not all. There are other variations in ground shaking intensity that come from other places than just distance. So for example, when I say source heterogeneities, that means that in the process of the fault rupturing, there could be places or pieces of that fault that actually slip a little bit faster, slip more. So that non-uniform slip field will lead to pieces of that fault producing more energy than others. So that is one source of spatial variation that we see there. Another one is because of the earth crust not being uniform, we cannot expect that at equal distances all around the fault rupture, we will have the same amount of reduction in ground shaking. So that's another place where you can already have that intuition that yes, if we have a more weathered rock, for example, then that one will create more resistance to those seismic waves. Those waves will be attenuated or reduced in amplitude. And then my personal favorite, local side effects, the effects of that near surface geology and deeper geological structures on that ground shaking. So all other things being the same, you can expect greater amplification of the ground shaking if you have softer soils, for example, because they tend to amplify that motion. So even, and this has happened and this has been observed and documented in multiple past events, even if you're far away from the source, you can still have very high levels of ground shaking if local side effects are such that amplify that ground motion. So this is why, knowing what I learned during my PhD, I knew that we have to account for all three of this to have a better understanding of that spatial distribution of ground shaking. Of course, it's not easy. So from my time in Alaska, and I should say you're coming with me to various places today. All beautiful places. I don't know if you've noticed, but when you have tectonic activity, you end up being in very beautiful landscapes and nice nice places all around. So Alaska is not different here. And again, I'm not sure if you can see it very well, but this is the map is showing the Anchorage Basin. And then I wanted just to point out to some similarities and differences in how the accelerations recorded from a sensor at all those different stations, how they look. And I will say that all of the acceleration values that I will show you today are coming from very similar distances from the source. So that path contribution should be the same. Source is the same. So now we're really looking at, okay, what is the soil, that near surface geological structure doing to the ground shaking? So just very qualitatively, we can see that the peak ground acceleration, or PGA, reported there are similar, 0.28 to 0.25. And then we have other ways to characterize frequency content in ground motion, but just by looking at the peaks and throws in the time series, they look pretty similar as well. Some seismologists can actually tell the frequency content there. I need a response spectrum or a Fourier spectrum to do it. Let's move to the other side of the basin. Now we are with we have a peak ground acceleration of 0.22, and the ground motion doesn't seem as similar to the others. When we go to the middle, we see an amplification in terms of that peak ground acceleration. Now we're up to 0.47. Same source, same path. The side contribution is significant, and it doesn't seem to be systematic. The contours there provide a very simplified way to characterize soils. And according to those, there are some differences, but they cannot quite explain the differences in the shaking that I'm showing you today. And same here, right next to it, we have a completely different acceleration time series. So these are the type of observations from empirical data that really motivate the research question of, well, how can we characterize this ground motion variation? While the amplitude of the ground shaking varies spatially, some of that variation can be explained or predicted by what's called empirical ground motion models. And these are built based on empirical data. So basically you have sensors that can be used globally, or I should say deployed globally, collect data globally, and then you compile all of those and create a statistical model, and you regress that data. That is the most basic and simple definition. However, physics-based ground motion modeling goes into that as well. So theory that can explain some of the scaling that those models incorporate in terms of magnitude, distance, and site conditions, those are constrained by physics. So it's not just a statistical regression. Having said that, there is still significant remaining variation that's not quite captured by these ground motion models. So I'll walk you through one of my favorite examples of how we deal with what we observe is not what we're actually modeling. How can we interpret that error, right? Because a model will be imperfect by design. So what you will see is that we actually look into those errors and see what are we missing. Is there a systematic trend in those errors? So what you see in the y-axis is what we call a ground motion intensity measure. Peak ground acceleration is 1, and you already saw it. It's just the largest acceleration in that acceleration time series. This one is a little bit different because now we are accounting for the response of many single degree of freedom systems. And then those we're going to call the spectral accelerations. So still an indication of that amplitude of that earthquake, how strong the ground shaking was. And then on the x-axis is going to be distance. What I told you earlier on with distance, do you expect the ground motion to increase or decrease? Decrease, going down. That sounds like a song. Okay, I did tell you that I get excited with this example. So this is start, but I'm not going to say promise. This example shows different observations from different earthquakes, parameterized with the same distance. So whenever you see a star, and I don't have numbers intentionally, I don't want you to be carried away by the details, but basically from 5 kilometers to 150, 300 kilometers, what you will see is a decrease in that spectral acceleration with that increase in distance. Great. I want to use these empirical observations to create a model. I did mention that I'm going to do a regression, statistical regression, nothing too cumbersome. It will be a function of predictive variables, and maybe I'll have this on. Those predictive variables will try to parameterize those source, path, and side effects that we talked about. You can think about moment magnitude or any other type of magnitude scale that will capture the size of the earthquake. Okay, that can be 7.1 for that Anchorage, Alaska earthquake. Now we want to characterize path. The easiest one is distance, source to site distance. If the earthquake happened 50 kilometers away, 100 kilometers away, 300 kilometers away, there will be a different scaling. So distance will be my other predictive variable. And then our favorite, site conditions, those have to be parameterized somehow. Those are also very complex. And one parameter that has consistently shown good correlation with intensity measures is one that's called shear wave velocity. And not just shear wave velocity, but an average in the top 30 meters. So we call it VS30. It's not perfect, of course, it's a parameter. And if you notice, it's only averaging a measure of stiffness in the top 30 meters. So what about the rest? It's imperfect, but it is one way that engineers have found to, and engineers seismologists, to characterize side effects. So once we draw that line and we have our model, we will have a model error. It will not fit perfectly all of my different data points, which was the expectation, right? It's just that now I can say that my observation, the observed spectral acceleration, is equal to my prediction plus the error, plus that difference. That's it. Now, I did mention that when you develop a ground motion model, you use data collected from many different parts of the world. Sometimes they can be regionalized, but usually they come from global data sets. So now in blue, you have one event. In red, you have a different event. And we could come up with event-corrected median predictions, which means that now I'm not interested in the median across all the different events. Now I want one for the Anchorage earthquake. Now I want one for the Turkish earthquake. And when we do that, we realize that there is a different error or a different difference between the median prediction and that of my event-corrected prediction. So I'm going to call those between event and within event. The between event piece will not matter too much for us. I wanted to focus on us correcting for whatever event we had, and now the differences that we're seeing from, let's look at the blue one, from the start to the event corrected median, that is coming from your site. We've already corrected for your source, and this is now changing with distance, so we have the path effect. Now, if we are not matching the observation, we're missing something about the site. I want to understand what it is. So in order to do so, I'm going to plot that error. I want to know the spatial distribution of that within event residual, because then I may be able to see if there is some correlation, some cluster of those errors. What I know from my geotechnical background is that soils are not just randomly distributed. There is something that's called the positional environment. And that really drives that heterogeneity that we see in soils. So we could really have an informed guess of where softer soils are, where stiffer soils are. So this is Japan. Now we go to another very highly active tectonic region. Japan is very special because it's a playground, a great lab for earthquake engineers. You have a seismic network that's unparalleled, in my opinion, more than 600 plus sensors, surface at the ground surface and at depth. Multiple earthquakes happening pretty much daily, and then a very interesting geology and a very good subsurface characterization of all those stations, all those sensors. So you pretty much have almost all the pieces of the puzzle. Keyword almost. So you have the recording stations. That means that I have those acceleration time series, and I can characterize it. I can use different techniques to understand amplitude, understand frequency content, and duration from those. I also know a few things about the site condition, like shear wave velocity. That's good. So with those two and additional ground motion parameters from the literature, I am curious to see if my errors that residual in my ground motion model are correlated to some of the spatial distribution that I see in the site conditions. So that's exactly what Christina did. And what you're seeing here is the distribution of within event residuals. So a few things to help you understand those two maps. So one thing that you may be able to see is that in the color bar, we have negative residuals and positive residuals. So going back to our definition, we have observed minus predicted, that's my error. So wherever you see negative residuals or blue, that means that your prediction was actually larger. You're over predicting the model that you're using. And I should say that this one is very specific to one ground motion model that we use, but we shouldn't see a large variation across different ground motion models. And then for positive residuals is the opposite, right? Your observed was now larger. So now you're under predicting based on that model. Something that really was interesting for us to see here is that you see some form of a spatial clustering of these errors of the within event residuals. And from that, our research is now dedicated to understand if the spatial clustering of the error in the ground motion prediction can be tracked down to the spatial clustering of maybe shear wave velocity, maybe that parameter that I mentioned, BS30, or others that are not in that ground motion model functional form, but should be, so that the overall error is reduced, so that we erase that bias that we are seeing here. So that's ongoing work. And you may be wondering, well, how can you understand spatial correlation from the distribution of all those within event residuals? Well, ideally, if we had all the budget in the world, all the time, and wonderful students that we could, then we would like to have multiple events recorded, let's say in Japan, at every pair of stations, so that now I can track the spatial and I can compute the spatial correlation at those two stations and multiple of them. And then that correlation will be specific to that pair of stations. I would not be assuming the correlation to be equal across any pair of stations. Of course, you can see that this is not practical. We cannot afford to have it. Maybe in a place like Japan, which is something that we are looking into, but not anywhere else, right? So in practice, what we end up doing is assuming a stationarity, which is nothing but simplifying the problem to, you know what, distance. If you're close together, you're highly correlated. If you are very far apart, you're not that correlated. For a geotech, that doesn't work because, again, the positional environment, side effects will not be random, will not be fixed. We have to do better. So while I understand the practical implications and why this is a good first starting point, I think that we can do better. And actually, you guys and your expertise have been very inspirational to try to get at that very boundary. So I already said, soil properties can be spatially correlated at nearby locations. That means that if they share common geologic origins, or even the tectonic environment, that can also be a big player in that spatial variation, then we could have a better correlation structure across these different intensity measures from the ground shaking. And then we can expect that the site response, and when I say site response, is that amplification or de-amplification of those seismic waves from the local site condition. So what our research is trying to do is challenging that stationarity assumption and trying to use our knowledge of geotechnical properties and geology to inform that non-stationary assumption now. One way in which we have tried to do this is by, again, looking at those errors, but now also looking at the distribution. What you're seeing here is a geologic map, superficial geologic map, which we have simplified as well, because in and of itself, it has a lot of complexity. So we had to come up with some grouping of different geologic formations, geologic groups. So in doing so, we started to see, again, some patterns in the data that I think can explain what we ultimately see in the ground motion variability. So what you see on the left is the variation of shear wave velocity. And I can appreciate that you don't see all the different colors, but softer sides tend to correlate with younger, less consolidated material, which makes sense. So it makes us think that even in the absence of shear wave velocity measurements, we could use geology as a proxy to get that information. So that's ongoing work. And then we've used some of these techniques to understand the spatial variation of ground motion, not this time getting into the errors in the model, but just how are the observed ground motions varying regionally. We did this for that Anchorage earthquake. That was part of our contribution to the reconnaissance team to provide a map of how ground shaking change spatially in the Anchorage basin. This one is showing peak ground acceleration again. It's widely used in engineering, but its value can be limited. Anchorage is a basin. So basin structures have or can have very thick sedimentary deposits, and thick sedimentary deposits can have a big impact on long period ground motion. So this is short period. Now I want you to see that there is a pattern with, and the basin is dipping on that direction where you see more red. The thicker the sediments, we do see an amplification of the ground shaping for this specific parameter that caters to long period motion. So going back again to the comment on frequency content matters, depending on which parameter you use, you will find a completely different spatial correlation, which has been also interesting for us to calculate. So that is my journey on ground motion variability. I did mention that deformations are equally important. So I will briefly show some of our most recent work on understanding those deformations. Of course, this will be related to earthquake triggered deformations. And this one in particular, it can be very pervasive, can be very damaging to civil infrastructure, and it's called liquefaction. So basically, soils are stronger because of that interparticle friction. The closer there are, the denser the packaging, the better. What happens is, if you have a saturated, so all the voids in the soil are full with water, and now this is a cohesionless material, so it's all friction like the sand, and now you shake it really, really quickly and hard, then you won't give time for that water pressure that's been generated to dissipate. What will happen is that water will become in between those grains and separate them. When they're separated, because the strength of soil is connected to that interlocking between particles, the soil will lose its shear strength completely. It will behave as a liquid. It just blows my mind how you can see that in the deformations after earthquakes when liquefaction happens. It does really behave like a liquid. And I have a picture that I think will really explain the phenomenon. But what's important about that, more than the science piece of it, is the deformations and the impact on civil infrastructure. Can you think about potential failure mechanisms? If your foundation soil behaves like a liquid, you have no foundation anymore, right? So that's kind of like what you see here. You can have some liquefaction-induced settlement, but you can actually have catastrophic failure because of liquefaction happening. Sand boils are another form of superficial expression of liquefaction being triggered. But then I was really curious about this one. Lateral spreading are really large ground displacements or lateral displacements happening because of liquefaction being triggered. They don't happen everywhere. There have to be certain conditions to lead to this type of specific deformations. And here I have a few examples for you. This is the one picture with the car. When I mean, liquefaction can be really, really damaging to civil infrastructure. But then you can see the cracks at bridge sites, ports, again, saturated, sedimentary columns, frictional material, an impulse type of loading. This is not your typical load. You saw those time series of acceleration. These are seconds of really large ground shaking. So the soil really doesn't have time to dissipate the energy, and then that's when liquefaction happens, and then these deformations follow. So because we're thinking about geologic depositional processes, how that affects ground motion, it has to affect ground deformation, right? They should go hand in hand. So Nancy Gaviria is the PhD student leading this project, and she has a major in geology. So she actually brought a lot of the research questions from her background, asking, well, in fluvial environments, can we think about how geomorphology affects lateral spreading? I said, I don't know. It looks like it should have some sort of impact, but nothing in the literature, or at least not in a quantitative way, was telling us that story. Some observations though, and today I should say these are some of the approaches that we've taken, looking at geology, statistical regression of empirical data. So we are going to come up with a model, and then some laboratory testing as well. But today I'm just going to show you some of the results on the geospatial analytics piece. So in red, all the lateral spreading ground tracks from the Christchurch earthquake. So now we're in New Zealand. Why New Zealand? It's a fluvial environment, and the Canterbury sequence 2010 to 2011 not only provided a lot of data in terms of ground motion, but they also had very good documentation of geotechnical properties in the Christchurch area where a lot of liquefaction was observed. So perfect case study for us. We had information we needed, like where the water was along the river. We wanted to focus on fluvial environments because that's where most of the data that we had is. And also because we could envision certain hypotheses that we could test with the data that we had. So it was constrained by both curiosity and availability of data. And then again, because of I would love to share all of our hypotheses with you, but I will focus on just one. We are looking at meandering rivers. The Avon River is that big, maybe I should go back and show you. The box on the top, that's where you probably may be able to see some of the meanders from the Avon River. So I will focus, we were focused on looking at what aspects of those meanders could lead to less consolidated sediment, that's bad for liquefaction, or I guess good for triggering liquefaction, more saturated deposits, less interlocking of that, or less densely packaged deposits. We were looking at those triggers of liquefaction and see if the geomorphology could explain more or less deformations in those places. So in this case, we look at the cut bank versus the point bar, looking at point bar, how they would have younger deposits, just less consolidated than the cut bank. Hence, we wanted, we're expecting more lateral spreading there. And then going back to geology, we wanted to see if we could pair our observations and the trends, the systematic trends or patterns in that data in the deformation data with the patterns in geology or geomorphology of the region. So this is our third hypothesis, the one that I wanted to show you, where we said, well, if you have active deposition, meaning that this deposit where this sediments were just deposited recently, the packaging is not very dense, they should liquefy more. So we should see, when that earthquake happens, larger deformations there than, let's say, in other areas with inactive deposition that we call it paleo channels that have not seen that flow in many years. So those deposits should have had a chance to consolidate a little bit more. So we should see less ground cracks there. And that's exactly what we did. And in this case, we used a line density approach where we were interested in measuring the density of those ground cracks across specific geomorphological features that we define a priori. And we were really, really happy to see that in red, you find a higher concentration of cracks. And those higher concentrations were very well correlated with active depositional environments. So there was the aha moment where like, okay, now we have a chance to regionalize those predictive models that right now they don't account for this fluvial environment and specific features of the fluvial environment, so that the prediction is actually better and it's now fitting more closely to the observations. So that's where we are at now, and we're hoping to incorporate what we learned through this hypothesis testing into a new predictive model, basically parametrizing what we saw and reducing those errors for the ground deformation model. So with that, I'm going to end with a few thoughts on how I think geospatial analytics can shape the future. Although I'm hoping that my case has been raised today. Breaking disciplinary silos. I think you guys have an amazing opportunity to be that common language. So that I'm from civil engineering, I can talk to colleagues in geosciences, I can talk to seismologists, I can talk to sociologists, and understand patterns in the data and what that means, in our case, to reduce seismic risk for a given community. That is unique, and I haven't found that opportunity in a different field or subdiscipline. So I think that you guys have a tremendous opportunity being in this program. And then facilitating multi-scale and multi-hazard modeling by creating those frameworks. And the idea here is not only analyze, but also integrate heterogeneous databases. So it's just crazy to me how I have a small field, but even there, it's kind of innovative to try to integrate geology with geotechnical engineering. And you would think, well, shouldn't we be doing that all the time? And then integrate that with damage patterns in our civil infrastructure systems. And even take it another step and say, well, who's in that building? How are those communities in those buildings using those civil infrastructure systems recovering from that very same earthquake? It took more than the seismologists to understand the magnitude, the distance, the earth crust deformation, more than the geotech trying to understand the contributions of the salt column to amplification, and then the structural engineer to understand the forces impacting those bridges, and the sociologist looking at, well, who was able to recover faster and why? So I think that the geospatial analytics group and frameworks can be really that glue that helps us achieve those goals. And then with that, my last example, Haiti. I did mention that it was very apparent to us that engineering wasn't enough in this case. We needed to understand many more angles to this problem. This was an earthquake that happened in August 2021, magnitude 7.2, so a large magnitude earthquake, close to Lekai and many other cities. Here the star shows the epicenter, 2,000 deaths. I must say that there are differences, of course, in construction practices, but those aside, this was a very important case study for our team, because here we were able to test how geospatial analytics was going to be helpful for those areas that were highly uncertain. Here we didn't have a large database of shear wave velocity values, but because we had confidence in how we could model and interpolate spatially how the site conditions were varying and how the ground shaking was varying, then we were able to produce an outcome that then others can use for planning and recovery efforts in the region. And it came again from that recipe that seems to be working for us, understanding geology, even in the absence of measured data. It was giving us important connections to understand the spatial variability of subsurface conditions, and then from there, how we can expect some variation in the motion. And then this is just for you to maybe remember, this was in the news for a while. Many different hazards and crises were happening at the same time, right when the earthquake occurred. And this is just the path of a tropical storm that happened, I think, 2 days after the earthquake, and it was simply just devastating. The other issue from the engineering perspective is that as an earthquake engineer, I only design for seismic hazards. I don't do hurricanes or storms, but in reality, these communities are and will continue to be exposed to multiple hazards that can happen at the same time. This also happened during COVID. Hence the need to understand the social dimensions constraining the whole impact of this event. So we came up in this particular work with a framework that really integrated engineering dimensions with social dimensions, understanding people being displaced by multiple crises and how that led them, unfortunately, to areas with a higher seismic hazard, because hazard was not part of the planning vision at the time. And this is one of the outcomes of our paper in this case, where we really looked at the displacement from the 2010 earthquake that you may remember, Port-au-Prince. People were still recovering from it. Unfortunately, NGOs and others in recovery efforts mobilized people or displaced people to the area of precisely the second earthquake in 2021, which did not help with the different failures that we saw. So how can geospatial analytics help? I think that these complexities have to be understood in a geospatial framework. It's not only our common language, but I think it is one of the right ones to understand all these complexities, and one that I'm hoping will help me integrate social dimensions as well, something that our lab will want to explore. And I promise this is the last one. I just know that students are here, and I wanted to share just some additional, not technical thoughts with you. Persevere is the first. This is really difficult, what you're doing, not only in your field, but just grad school in general can feel frustrating at times. But remember why you loved it the first time and persevere. Find that those supporting mechanisms to continue. Bring your authentic self. I'm from Venezuela, Latin female faculty member, and I know it can be difficult, but if you find your voice and you are strong to bring it to every other aspect of your life, I think everyone will be happier and better for it. Everyone will appreciate it. Do what you love and put the time and effort. We do need your time and effort to succeed. And then be curious. If anything, and hopefully more than that takeaway, but if you can only learn or remember something, stay curious, because that will lead to wonderful experiences in your life and hopefully discoveries that can change other people's lives. Thank you.
Thank you so much, Ashley. We have time for a few questions. The audience and the online audience as well. You can send a question in the chat. The audience mics are on, so
okay. Quick question. I was wondering, like, have you considered including INSAR data and like calculate with your peak count acceleration data to see like where you are getting more damages?
Yeah, absolutely. This is the second phase of that project that I showed by Nancy Gaviria. When you're developing this prediction models, you have to build a consistent uniform database where you can identify these groups of or categories of different contributions or different effects. So for lateral spread in particular, all we have historically is people like me in these reconnaissance teams going and measuring. And you can imagine how non-uniform that process can be. But I think remote sensing can offer an opportunity to have more consistent data that we can use in our modeling approaches. So yes, we are definitely considering that for the next stages. Thank you.
Yeah, so I'm curious about in a built environment like Christchurch, how do you get detailed paleoenvironmental data? I can imagine there's lots of geotechnical borings, but in my experience, I'm thinking back to a project Carl and I worked on, trying to use geotechnical borings for geologic purposes is very challenging because that's not their focus. Are they doing better there? Or you got some other data set? How do you pull that out? Do we need a bunch of radar profiles or what's the solution?
It's a struggle. I hear you, and this is why I feel like we need more interdisciplinary efforts, because of the surveys that I run as a geotech. I have not those applications in mind. So we ran into the same issues, and this was mostly coming from maps, historic maps. And Nancy did an amazing job interpreting and actually finding, places where they were not identifying the same formations or the same features. So whenever we weren't sure or we couldn't find the same feature in 3 of them, then we didn't include that in our analysis. So we had some quality control in that regard, but we don't have any specific measurements. Yeah. Some people have encouraged us to go and take those ourselves. So I don't know. We haven't tried that yet. It's expensive to go to museum. Yeah. But no, you're absolutely right. The data, as you're trying to integrate it becomes very apparent that different applications will have different depths, different resolution, and then once you're trying to learn from all of them at the same time, it's not a trivial task. Other questions? Who's ready to become an earthquake engineer? I'm recruiting. Good.
All right, with that, let's give Ashley another round of applause.
Oh, sorry, and Cristina Lorenzo Velasquez, Carl, 46.7 kilometers is the focal depth for Alaska. Thank you, Cristina, you're awesome. I'm telling you, student. Thanks, Cristina. Bye, everyone. Should I end here? Yeah, no?